All right. There we go. All right. So yesterday we looked at, you guys, the bond length, bond energy, electronegativity, and types of bonds. We're going to do a little bit more with that part, the electronegativity and the polarity of bonds. Okay, that's the videos you watched. I went through then, and we went through and did VSEPR notation, steric number, and resonance. I'm not as worried about resonance right now as we'll get more of that and check those things later. So today, like yesterday, I said that the VSEPR notation, the steric number, are key to what we're going to do today, and we'll see what those ties are. Now, up on the board here, and I think it's big enough for you guys to see at home, I've got the some definitions that I'm going to go over. I'm going to have you sit in the very back. That way I don't have to worry about contact tracing if anything happens.
You don't have your camera on.
Oh, crap. Thanks. So you've got here's the terms. I think you guys at home should be able to see them. Is that big enough? Now, I'm going to talk about these. It's going to be a little vague until we start applying it and what we're going to do with an activity today. And to be honest with you, I'm probably going to work, I'll probably go over this stuff about 20 minutes or so, give some explanation, 20, 30 minutes. The rest of the time I'm going to give you to work on the activity, which I want to be complete before class next time. Okay? Now, top here. Not a term I'm going to use a lot, but I will use every once in a while. I've got some documents that I may use that use the acronym HEDA, which for us means high electron dense areas. And that's pretty simple. A high electron dense area is simply going to be a bond or a lone pair of electrons. That's it. Now, we don't make a distinction with a high electron dense area between single, double, and triple bonds. We treat those as just all equally a high electron dense area. The reason why is because, as we will see shortly, how electrons repel and the shape that molecules take really doesn't matter there's no real difference between double, triple, and single bonds. Really, the only thing that matters for that, or that would make a difference, is the bond energy and bond length. But the geometric arrangement that they take isn't affected by, or hugely affected by, single, double, and triple bonds and the difference between them. So we're going to treat a high electron dense area as just a general bond or lone pair. Now, I think I might have said it in class yesterday, but I want to make sure you have it in your notes someplace. Give you a chance to open them up to the slide that had the VSEPR notation and the steric number part. Because I've changed these notes from the past, and I didn't care for the slides and stuff I had regarding this material, so I just didn't use them. So VSEPR, so that VSEPR notation. VSEPR stands for, ready? Valence shell, electron pair repulsion theory. So valence shell, electron pair repulsion theory, which The reason I give that definition is because everything we're going to do today revolves around that basic idea. We have electrons that covalently bond or exist as lone pairs around the central atom that will give it a three-dimensional structure. That three-dimensional structure is determined by how they repel each other. So when you get the chemical bond to form, when you get that electron cloud to form, they overlap, and you form those bonds, and you got one cloud where electrons can go wherever, those electrons are going to distribute themselves, those atoms are going to distribute themselves to minimize the repulsions between atoms. Okay? Now, hold on a second. There we go. Now, these high electron group areas arrange themselves based on their geometry and their groups of electrons. So our high electron dense areas are going to be groups of electrons. These three terms here are all the same thing. This is one of the things that in chemistry that every textbook may be a little bit different. The basic idea is the same, but the textbooks are going to call them by different names. I learned it as electron group geometry, or just group geometry. The online modeling thing we're going to use today, and I'll show you that in a couple minutes here, they call it electron geometry, which kind of makes sense. I kind of like it because what it's telling us the geometry that the electrons take around a molecule. But these three terms here are interchangeable. Now, I reemphasize that these group geometries, the electron geometry, electron group geometry, however you want to say it, they include any electrons, whether they be part of a bond or whether they be part of a lone pair. Molecular geometry is related. These two, the electron group geometries and molecular geometries, they are related to each other. What's different would be the name that we apply. So, molecular geometry, the name may be different than the electron group geometry because in the molecular geometry, we only include bonds, not lone pairs. Okay. Now, to tie in with what we did yesterday is if you can determine the steric number, you will know the electron group geometry. And I think when you did the steric number and the VSEPR notation, you saw that you got, you got limited combinations. And the steric numbers are either going to be 2, 3, or 4, very rarely 5 or 6. And I'm sure you found a lot of 4s, right? Okay, because that's a very common structure. If you have a steric number of 4, every molecule, or every shape is the exact same shape. So you know it's steric 4, you know what that shape is. Because there is a difference between our electron group geometry and molecular geometry, the VSEPR notation is going to be related to your molecular geometry. Because the steric number, remember, didn't distinguish between lone pairs and bonds. It was just counting them all. And that's what electron group geometry does. It just counts them all. Bonds and lone pairs. Molecular geometry only includes atoms that are attached to the central atom. Well, in our VSEPR notation, we differentiated that with the X and the E. Okay? So the VSEPR notation is going to be related to the molecular geometry. I will tell you this. Every structure that has an AX2E2, doesn't matter what the molecule is, they will have the same molecular geometry. Okay? Questions so far? About any of these definitions, anything I said? Yeah.
Can you explain to me how you find the steric number again?
So, are you good with the VSEPR notation?
Not really.
I'm going to be doing water anyway, so I'll just put it up here. The X represents your bonded atoms. So there's 2 atoms bonded to this hydrogen, so it'd be AX2. And then your E is going to be how many lone pairs of electrons you have on the central atom. That would be 2.
Okay.
Your steric number is just the sum of these 2 then.
Okay.
Okay?
Thank you.
Questions? Others? All right, so in Canvas, go to the document, the page for today. People at home, you should see on the Zoom session a little model thing that I'm turning around. Is that correct? Okay, so in Canvas, for the today's page, you should have, there's a link to the PhET molecule model, something, I can't remember what I titled it. It starts PhET, P-H-E-T. Click on that. On your iPads, you should get that web page. Everybody good? Now, I don't know why. I think it's because I got so much crap plugged into my computer that it's running in low resolution mode. Your atoms and stuff aren't going to be pixelated like mine are. But it doesn't affect how I'm going to explain stuff. You have 90 seconds to play with it and get it out of your system. It's not working?
My friend can get on the Zoom.
Your friend can't get on?
Yeah.
Now you get 90 seconds to play with it, get out of your system. Check boxes, uncheck boxes, things like that. So this is from the loading spot?
No.
Oh, it's keep in mind, you can add a whole bunch of stuff to these atoms. It doesn't make the structure correct.
what she says.
Okay. You've had your chance to play around with it. So I am going to do so. Okay, so here's some explanation. So I just got done describing the VSEPR theory, valence shell electron pair repulsion. And the basic idea is that your atoms that are bonded in lone pairs are going to get as far away from each other as they possibly can. They're going to repel each other. If I have two atoms, like this molecule here, so if you hit, make this, hit reset, add just two atoms. Doesn't matter if they're single, double, or triple bonds. I'm just going to go with single bonds. No matter what I do to this, if I move this quickly, I can make it bent. I can bend them so that they're not 180 degrees away from each other, but they eventually go back. And the reason why is because if I bend them and they get closer together, that means the repulsions have increased. This arrangement is the furthest away those bonds can get from each other, and that minimizes the amount of repulsion between those atoms, the electrons that are in the bond. We're minimizing the valence shell electrons repulsions. That's why we shorten it, because it takes a long time to say that versus VSEPR, right? Now, I'm going to go ahead and show the bond angles. So you can see on this that it's showing that it's representing that we've got 180 degrees between those two bonds. Now, I don't know how much geometry you guys have been taught in the past, but I know it's not a lot if you're not in geometry, but it should be in, the only geometry I'm talking about today should be pretty basic. I think it's enough that you have covered it already at some point. So if you watch carefully, or if you do this on your own, if you try to bend this thing and make them closer, so yeah, you're going to successfully make that angle smaller, but it always goes back to 180. That's due to that repulsion. Now that's only two atoms attached to the central atom. If I add another bond, I change my angles. Because what we've done is we've added another set of electrons, another high electron dense area that's going to start competing with and repelling the others. Now, it's three-dimensional in structure, but pretty flat, so almost two-dimensional. Because if I get it like this, you can see these are all on the same plane. Okay? But they're 120 degrees away from each other because that is the furthest away, or that's the closest they can get, and reduce the repulsions. Or I guess you could say they're the furthest away they can get with reduced repulsions. Because if I try to rotate this upwards, okay, so if I make this go up, I may make this angle between the two atoms shorter, smaller, get them closer together, and increase the angle between these two. But if I increase this angle, I'm going to increase the repulsions over here. Well, you're thinking, well, Mr. K, pull it down, okay? If I try to pull this down, I'm going to make all of the angles closer. So this is the 120 degrees. That is the least repulsions that are going to occur between the atoms. Is you having any luck getting in?
No, it's still not working.
Okay. I just sent her an email with the link. Have her try that.
Okay.
All right. Now, what happens if I slap a lone pair on there? Well, I'm going to take off one of those single bonds, go back to the 180 degrees, and if I put a lone pair on there, so it's not a bond, I essentially get the same thing. Now, they don't, in this diagram thing, they don't show the angle between the lone pair and the bonds, but it would be 120 degrees. Good enough. So this is what we're talking about with the high electron dense areas. Let's talk about earlier when I was talking about the molecular structure. The structure just depends on what the electron groups. It doesn't depend what they are. They're all going to repel each other, and we're going to treat them as if they were the same. Now, full disclosure, if I had a lone pair of electrons versus a bond, technically, this angle would be a little bit different. Lone pairs of electrons don't repel the same way as bonded electrons. There is a little bit of difference. We're not going to worry about that difference. Okay? Now here's where we get to a more three-dimensional structure. It's where, I hate to say it, lose some people in terms of the understanding and being able to visualize it. This model, the digital models that you're making here, they're really good. Okay. Tell her to watch the videos. Okay. She'll be all right. So one of the things is that you know yourselves pretty well. Can you visualize in your head three-dimensionally? And some people can, some people can't, some people are sometimes, depends on how complex the thing is. So to help you guys out that are here, and for those of you who are at home, I'm going to have them on next week as well. I've got models of all the different shapes that you guys are going to encounter, physical ones, because it does help to come up and hold one and say, okay, this that I have in my hand is the same as what's in that diagram. I'm going to switch to my camera here for you guys at home. So, share. One. There we go. So that model that I had drawn is this. I know it's a little blurry, but and I know even on screen it's a little bit different, but if I hold it like this, you can see it's got three-dimensional structure to it. Whoa, there we go. This we would call a tetrahedral. Why? Because it's got four sides. 1, 2, 3, and then the base 4. That's the shape. Okay? Let's switch back to the program. So again, I'm going to switch one of these out for a lone pair and see that we still have that same basic structure. Okay. Now, this is where we get a distinction between our molecular and group geometry. So down in the bottom left, I'm going to turn on the electron and molecular geometry so we can see what those are. And we can see that they're different. In this molecule, I've got 4 high electron dense areas. They're all going to be 109.5 degrees away from each other. The basic structure is what we call a tetrahedral. But I'm going to take off, I'm not going to take off, I'm going to not show the lone pairs. So I just turned that off. So our molecular geometry is based only on these atoms on the screen. And that shape is a little different than that shape. That's why they have 2 different names. If I take that lone pair off and add a bond, you'll see here that the electron group geometry and the molecular geometry are the same. Because remember, the molecular geometry is basically describing the shape based on atoms bonded. And I have 4 atoms bonded. I got 4 high electron dense areas. Electron group geometry is based on anything, bond and lone pair. Well, they're 4 bonds. They're going to be the same name because they have the same structure based on what they're counting. But again, if I take off that singly bonded atom and put a lone pair, my name changes because molecular geometry only takes into consideration bonded atoms. And that lone pair is not a bonded atom. Questions? Okay. So in Canvas, you got a link to the VSEPR theory activity. Go ahead and open that up. Now, I know that I have a couple of people from Mr. Milligan's class. And we found out, dawned on me last period, that Mr. Milligan had you guys do the Lewis structures for about, I think it was like 24 molecules or something like that in that assignment he gave you last week. I think it was last week. Yeah, last week. And then I gave you the Lewis Structure 2 document. So in part A here, it says you're going to draw Lewis structures or redraw the Lewis structures for each of the compounds in the table. Refer to the number since you already have most of the Lewis structures done. So down here in the table, I've got the compound, and then I've got the letter that corresponds, is it Lewis Structure Document 1 or Lewis Structure Document 2? And then the number next to it to tell you which one it is so you don't have to go searching everywhere for it. So you have the Lewis structures done for the majority of these. Now, Mr. Milligan students, for example, your document that you had, the first document, I know you did not have silicon disulfide, the very first one on here. So if you don't have that compound, you're going to have to start from scratch with it. I don't think there's that many of them, but there are a few. Okay? So most of these you have already. A couple of them are new, and they say new. So you're going to have to draw your own Lewis structures from scratch for those. Oh, you know what? Okay, I need to do this real quick. Let's see. Format, text, subscript. Nope, not superscript. So this compound, and there's a couple of others if you keep scrolling down, would actually have multiple central atoms. So when you're doing these, you're going to include or a VSEPR notation, shape, all that stuff for each atom that can be considered a central. When you get to the point where you're doing those, I can help you out with that. Now, you're going to use the FET site where we're making the models. And you're going to make the models based on your Lewis structure. Make sure the number of bonds is correct. Make sure the lone pairs are correct. And use the information that you are given to be able to answer the other parts. So you're going to have your Lewis structure. You're going to put your VSEPR notation and steric number here. You're going to use the FET site to determine your group and molecular geometries. That's where you're going to go through and you're going to look at down here in the bottom left. Okay, my molecule geometry is trigonal pyramid. My electron geometry is tetrahedral. That's the things that you would fill in here. I call it group geometry. The program called it electron geometry. Remember, 3 different names for the same thing. And last, you're going to, well, not last, you're going to fill in the bond angle while I'm here. You're going to leave polarity blank for now. This is something we'll either begin on Wednesday, and if I don't on Wednesday, it's like, I'd probably give you guys like a 15, 20 minute thing to do. It's not going to be anything big if I have time to set it up. If not, then we'll just start in on class on Thursday. Okay? So you're not going to be filling in this last column with polarity right now. The last thing that you're going to do is you're going to include the bond polarity for each bond. So every bond, you're going to represent the polarity somehow. Now I'm going to show you how to do that. If you scroll to the very last page in that document, you're going to see that I've got the electronegativity values that you learned about yesterday, and we're going to use those to determine the bond polarity. So if you were to look at that table, you would find that oxygen has an electronegativity of 3.5. I only know that because I use it so often. Hydrogen has an electronegativity of 2.2, both of them. Ethan, I know you got a sibling, right? I know you got an older sister. Is that it?
I was the younger one.
You got a younger, oh, you're a middle, you got an older sister and a younger sister? Oh, I'm sorry, man. You okay? So, if mom and dad gave you 3 one cupcake and told you to share, who gets the most? Be honest.
Oh, me.
No. Your older sister let you have more?
Yeah, 'cause I'm the only boy.
Oh, jeez. You tell your sister, Mr. K says she's not doing her job right.
I will.
Okay? The true nature of it is the oldest should always get more. Right? I got a little brother. I didn't give him equal amounts. No way. I gave him enough to where he wouldn't go rat me out. So that's what your sister should do. So if we got a cupcake, I'm going to cut it in 60-40. And if he whines about it too much, maybe I'll give him like 45-55. And I get the 55. Because he was dumb and he couldn't do math right. Okay? So same basic idea here. We've got electrons that are being shared, but they're not being shared equally. Oxygen's like the big brother or big sister. It's got a larger value, it's going to get a larger share. It's going to attract the electrons more strongly. So to represent that, the electrons are going to be attracted to the oxygen more strongly. We put an arrow on the bonds to represent that those electrons are going to shift to be closer to the oxygen. Now, next time we're going to talk about polarity of the molecule. Yesterday, you learned about the polarity of the bond, where we have an imbalance in charge here, and what that does is that makes this end of the bond with oxygen slightly negative, and that makes the hydrogen here slightly positive. What do opposites do to each other? What do opposites do to each other? They attract. So if I had another water molecule and my oxygen's negative and the hydrogens are positive, could we get those two water molecules to attract each other? Absolutely. That's why your water is liquid at room temperature. That's the polarity of the molecule. We'll talk about that next time. Okay? Or maybe like I said, maybe Wednesday. So in preparation for that, on your Lewis structures, I want you to draw the arrows to represent the polarity of the bonds. Okay? Draw Lewis structures. When you're drawing them, I think in the instructions, it said try to draw them so that they represent the three-dimensionality that the molecule actually has. You don't have to be a perfect artist and draw it like it is on the screen. Still use letters and lines and stuff, but like this is water. It's got a bent structure. Don't draw it in a straight line. That's misleading. Okay. So you're going to draw them, put the arrows on the lines. You're going to determine the VSEPR notation and the steric number. All of those, with the exception of the arrows, all those things you've got done already. You came in today with the VSEPR notation and steric numbers. On Lewis structures, you already had done. Okay. Make them on the model kit, on the digital model, and then fill in what the molecular shapes are and angles. Quick note. If I had a compound like this, this does not have a single central atom. It's got what we would consider to be multiple central atoms. So I would kind of designate this carbon 1 and this carbon 2, all right? And what we would do is we would then look at and say, okay, I want to know the geometry around this carbon. So we would look at that. We look at this carbon, and these two hydrogens. And this would be our central atom. We do our VSEPR notation and stuff for that carbon. Follow me on that? And then we would do another one. We'd look at what is it for this carbon, and we'd treat that carbon as the central atom. That's why in the grid, you'll see some that have C1, C2, oxygen 1, or just like a separate oxygen, because you may have multiple central atoms. Questions about that? Okay. So go ahead and get started. Those of you at home, you're more than welcome to stick around. I will leave the Zoom session on. So if you've got questions, you can ask, and I can come up to the board and help explain things to you if need be. If you think you're good, then you're welcome to go, because the rest of the time I'm going to give for work. Okay? There's no excuse for not coming into class next time with these things done, because you're going to have almost about 50 minutes to get these done. And you're going to get a majority of them done. Okay? Questions? Okay. Get started. And I'm going to stop this.